Thank you very much. Very pleased to have been invited to come down to Dorking, and I hope over the next hour or so I'm going to just give you a tour through the geology of Morocco. It's an area we've been working on for 25 years with a group of PhD students, and I've listed some of them on there: Ord, Ivan, Nadine, and Kat. So we've been working on the geology. We've generally been funded by energy companies, trying to understand reservoir systems in Morocco, trying to understand source rocks in Morocco. Morocco doesn't have a lot of oil and gas, a couple of small fields, but they've been looking for a long time, and we're trying to help them find their own oil and gas. But also we look at these areas because they're very good analogues for other places in North Africa as well. So Morocco does have fantastic geology at outcrop. It's also a very safe place to go. So I hope I will also encourage you all, if you haven't been to Morocco, to go and visit Morocco, because I think it's a fantastic country. So we'll start. So we'll start with just locate ourselves. Give you an idea first of the size of Morocco. It's a bigger country than you think. I think it's twice the size of the United Kingdom. The northern part of Morocco, because it's in the south, you've got Western Sahara, which Moroccans believe is theirs, and they claim right to that area. So we're going to focus on the northern part of Morocco. So this is a satellite image of the northern part of Morocco. So just to locate yourselves, there's Tangier, Casablanca, you've probably heard of. You've got Agadir, and there's Marrakesh. And actually, what we're going to focus on really is this area between Marrakesh and Agadir. And if you look at the geology there, you can see the Landsat image. So we're focusing on that area in the middle. And if we zoom in on that, what you can see then is we have a very large mountain chain, which is the High Atlas mountain chain, which runs sort of southwest, northeast. It then splits as well into the Medelt area through here. And to the south of that, you have another older mountain chain, a Paleozoic mountain chain, which is called the Anti-Atlas. So what I'm going to be taking you is a tour from Marrakesh, which is where we often start field trips because it's a very easy place to get to from London or from Manchester. I'm going to take you into the High Atlas first, and then we're going to go down towards Agadir in this area. So that's the outline of what we're looking at. So as we go from Marrakesh, we're going to be going up into the High Atlas, where the Carboniferous and Triassic rocks are exposed. And then if we move towards Agadir, we can also see those rocks on the other side, and then we're going to move it to younger rocks. In terms of the geology, there's the geology map for that same area. And if we just focus on the three main rock types I'm going to be talking about, the ages, I'm going to talk about the Triassic rocks, Jurassic, and then the Cretaceous. So the High Atlas, you can see running through here. The High Atlas, at outcrop, it's dominated by the blue rocks in here, which are the Jurassic. But as you come further to the southwest, we've got Triassic rocks at outcrop, and that's what we're going to look at. In the middle, we have this area called the Massif Ancien, which is an uplifted block, Precambrian rocks right at the surface. And then on the other side of that block, we go back into the Triassic. And then you can see we can go from the Triassic, the reddish colored Triassic, then into the blue Jurassic, and then eventually into the Cretaceous. So that's what we're going to look at. Just to point out again, to the south, you've got much older rocks. These are all Paleozoic. So these are Cambrian, Ordovician, Silurian rocks to the south. And then to the north, and actually where Marrakesh is as well, you've mainly got Cenozoic rocks at the surface. Okay, yeah. So in terms of stratigraphy, we're going to work, as we should do, we're going to work in a sort of logical order from the oldest rocks to the youngest rocks. And what I want to also show you in this talk is how the geology changes as the basins change, because it's to talk about how these basins have evolved. And we're going to talk about how it evolves from a rift basin, which it is in the Triassic. So it's a basin dominated by faults and rifting. And then we have a position in here, which we call the breakup unconformity. And this is the point at which the Atlantic Ocean started to open. And when the Atlantic Ocean started to open, the rifting stopped, because then we were creating oceanic crust. So all the tension in the system disappeared. And then above that, we go into a section which eventually becomes very dominated by carbonates. So we see two very different systems. We see an older system, which is dominated by sandstones, clastic sands and mudstones, red rocks. And then once we have the opening of the Atlantic, we go into a younger system in the Jurassic, which is dominated by limestones, because now we have more marine conditions. And I want to show you how that evolves through time. Now, I won't have time to talk about it, but another big reservoir in offshore is actually the Cretaceous. We've worked a lot on the Cretaceous as well. It's also sandstones. But we're just going to, in this talk, we're just going to focus on the Triassic to the Jurassic. Okay, you can do the next one. And so that I've just made that bigger. So if you couldn't see it properly, we can all see it. So we'll have a look at these, what these basins look like, these rift basins look like, and they're full of clastic sandstones. Then we'll have a look at the basalts, and then we'll have a look at the limestones above. But I also want to show you why we go from a basin that is rifting and full of faults, and why the faults stop, and then why we go into a basin which is dominantly marine, and what we call a post-rift basin or a passive margin basin. So if you want to go to the next one. And to set the scene, just before the Triassic, of course, at the end of the Carboniferous, the two giant continents, Gondwana to the south and Laurasia to the north, those two giant continents had collided, and they created the Hercynian mountain chain, the relics of which we still see in Scotland or the Appalachians. And so I'll put a red cross for where we are in Morocco, but this is the UK as well. So UK is also on this sort of mountain chain, which actually splits into a few arms. So at the end of the Carboniferous, this collision of these two huge continents had produced a very high mountain chain. And then what we're going to see is this is the breakup of this supercontinent. And the supercontinent, when these two joined together, became the supercontinent called Pangaea. You've probably heard of Pangaea. Okay, next one, please. Now, I'll probably have to flick through these. I will flick through these. So this is not my work. Now, this is work courtesy of a person called John Teasdale, and he's built a series of plate models which show how these plates have moved over time. So we're going to have a look at what happened after the Carboniferous when this supercontinent started to break up. I'll flick through them. I'll do it from here. Yeah. So we start off on here, and what you should be able to see is you've got where Africa is, we've got Canada, North America, and the Caribbean. Now, what I've done is they're very complicated because each of these colors represent different basement types, different types of basement. And these are basement types that accreted together largely in the Precambrian. But if we simplify that to start off with, so what we have then is when Pangaea formed, we have the area that is now Africa, the area to the south, which is South America, the area which becomes the Caribbean plate, and then the North American and Canadian plate. They're all welded together. They've all been pushed together. But Pangaea became unstable. And so eventually everything then starts to break up and rift. So we'll go through that now and see the rift phase. On here, the black lines, these black lines that you see here, these are the position of the faults. So you can see we've got a whole series of faults. If you want to imagine what this was like in the middle of a continent, you need to think about the East African Rift today. There's a rift in Africa today called the East African Rift in the middle of Africa, because Africa today is being pulled apart. So this is what was happening in Pangaea The whole of Pangaea was being pulled apart, and we had a whole series of faults all the way down here, big rift faults. And you can see as you come up to Morocco, which is right in the north, you can see it splits into two. So this is where the Atlantic now forms, but this is the high Atlas. So in the Triassic, it could have gone either way. Maybe the high Atlas would have been the main ocean, but eventually we'll see that what happens is it breaks here, so the high Atlas eventually stops moving. So we can flick through these slides. So you'll see it start to move. If you look on the top, you can also see the age in millions of years, and the stage this is the stage in the Triassic is the Norian. So it's moving apart, and then you can see that now we're in the Jurassic, Plains-Bacchian, okay? And now you can see we're just starting, in this area, we're just starting to develop oceanic crust. So we've got marine waters flooding in through here. Very narrow basin, something like the Black Sea today, also the Caspian and Black Sea today. Very narrow basin. But what you also notice is all the faults have stopped. Because once you break the crust and you create oceanic crust, it's a bit like pulling apart a piece of paper. Imagine you're holding a piece of paper and you're pulling it apart. It's all under tension. But if you cut it with a pair of scissors, you can move the two sides away without any problem. So this is what's effectively happened. We've broken the crust. We create oceanic crust through here, and the rifting stops because there's no more stress in the basin, and we can move it apart. And then, as we'll see now, over time, the Atlantic just gets bigger and bigger over time. So we're going through the Jurassic. You get very big. You notice it's happening in the north and central Atlantic. But if you go further south, down to the south, down here, the South Atlantic is still not here. South America is still attached to Africa. Then we go into the Cretaceous. Now in the Cretaceous, and then in the Cretaceous, you'll see South America start to rift. And then eventually South America moves away from Africa. And then we produce what we see today. That's not quite the end. We're still in the Cretaceous. So we've seen that. I'll just go back one more time so we quickly show you that again. So what we've seen is rifting in the Triassic. Maybe go back a bit further. There we go. All these rift faults in the Triassic. And then in the Triassic, these areas that were subsiding, we're in the middle of the continent, right in the middle of a continent. There was no marine water could get in there because it was in the middle of the continent. But then when you get to the Jurassic, we start to open a connection to the north, to Tethys, and marine waters flood in, and then we generate an ocean, a small seaway first of all, and then eventually we generate an ocean. And then later on, South America, and then the South Atlantic opens. Okay, so we're going to have a look at the Triassic. Probably many of you, if you've been down to the south coast of England, you've probably maybe been to Sidmouth or Budleigh Salterton. You've seen the Triassic down there. If you're in the north of England, we go to in the Wirral or on the coast in the Wirral. So in the UK, we have very similar rocks in the Triassic. The Triassic is famous all over the world, well, most of the world, everywhere, for being red. Because there were rocks that were deposited in the middle of a huge continent. The analogy today would be thinking about Australia. The middle of Australia is a dry continent. And the middle of Pangaea was a very dry continent because it was a huge continent. So it's red rocks. So in Morocco, where the light yellow represents the sandstones. And we see very similar sandstones in Canada. We see similar ones a little bit younger in Portugal. We see similar ones in the UK. They're not always exactly the same age, but they're very close in age. And then what we see is we go from a unit that's dominated by sand to a unit that's dominated by mudstones. And then certainly in the Atlantic, we have these basalts forming as we break up the continent. So go to the next one, if you want, sorry, if you do that. So we're going to go from Marrakesh, and we're going to go into the High Atlas. So we're going to look at the Triassic in the High Atlas. Next one. So we would drive from Marrakesh. I think the next one will make it go yellow. And this is the road you would take. Next one. There we go. So there's a road you can easily drive. It's not a motorway. It's a nice road, though. You can drive up through Eureka, and then you start to climb. In here, we start to climb into the low foothills of the Atlas, and then we can drive further up, and we're going to go to this place called Ukmaiden at the very top. Not the highest point of the Atlas, but we're in the mountains when we get to Ukmaiden. The line here runs through here. This is what's called the North Atlas Fault. So this is the northernmost limit of the big faults that produce the Atlas Mountains. Everything north of here is very, very flat. And then you have the mountains on here. So the next slide will show that. So this is the North Atlas Fault. And then there's many, many faults in here. If you go to the next slide. And this is what it would look like if you were in Marrakesh driving towards the Atlas Mountains. So we're in Marrakesh, we're looking north. So you can see the Atlas Mountains in the distance, often snow-capped even in the early summer. The North Atlas Fault is running somewhere through here. And initially you get these low hills, and then eventually you start to rise up into the big mountains of the Atlas. So we're going to drive through here, and we're going to have a look at what we see first in these low hills, and then drive up further through here. So the next one will show that. So we're going to go from Marrakesh, which is it. It's got tertiary or quaternary rocks in Marrakesh. Drive up this road over the Atlas Fault and up. And if you see what that is on a cross section as we're driving, the reason these hills are here is because all this area in the Alpine, so much later, this area was squashed again in the Alpine. And that compression forced the Atlas Mountains up, and they were pushed up, popped up. And so we have the low hills, and then up here we've got Precambrian at the surface now. Next one. So the first place, if we go over the Atlas Fault, we drive in through here, and then we end up in some Carboniferous rocks. So these are the rocks that were there before the first big mountain building in the Hercynian. So if we look at the Carboniferous, which is the next slide, you can see the Carboniferous is, they're deep water mudstones, and you can see they're very heavily folded. So this is good evidence that after the Carboniferous, or at the end of the Carboniferous, this whole area was compressed and a big mountain chain was developed. So these rocks have been uplifted and intensely folded. And sometimes in some areas they're even metamorphosed, but they're in sort of slate facies. Now, in terms of hydrocarbons, if you're looking for a source rock, these are not the sort of rocks you want to look at source rocks for, because they've been buried quite deeply and compressed and folded. They're not so good. Okay, the next slide, we will then move to keep driving along the road, and then we enter this sort of salmon color. This is the Triassic. So these are the Triassic basins that were sitting on top of that. So after that mountain building, this area then started to subside, and the Triassic was deposited on the top. Okay, so we're going to go to here. And this is what we see. So here we see these fantastic red rocks of the Triassic. All these rocks are Triassic in age. And you can see they're not intensely folded. These have been tilted, but they're not intensely folded. And they rest on top of much older rocks. And there's an unconformity through here. So I think the next slide will make a line come on here. Yeah. So actually, in this location, even the Carboniferous has been eroded away. So when we had the mountain building and the Carboniferous got uplifted, the Carboniferous got eroded away. So here we have Triassic rocks sitting on top of the Precambrian. A big time gap, a big amount of erosion. Probably along this unconformity, Cambrian rocks were removed, or Ordovician rocks were removed, and then eventually even the Carboniferous was removed. So we'll have another look a bit more at the Triassic. Yeah. Next one should take you somewhere. Yeah. So the reason we looked at the Triassic, I know we've got a few petroleum geologists in here, is because within the Triassic, we have reservoirs, potential reservoirs for oil and gas. People are now also looking at these as being potential reservoirs for other things. So, and the most sandy unit is this unit in the middle. So we had a PhD working on that. So the next slides just show you some pictures of the rocks in that sandy unit. So this is this really sandy package, especially this package. If you keep flipping a bit, yeah. So we've got, it's called the F5. So the unit below, which is also Triassic, is much more muddy. And it has some very thin sands. You can just see some sands coming in. But when you get up from the lower up mountain into this one is very sandy. It's 100 meters thick. It's got a net to gross of nearly 100%, 95%. This is exactly what you want to find in the subsurface if you drill a well for hydrocarbons, or if you drill a well and you want to put carbon dioxide in it. You want to find a sandstone like this. Okay, next slide, please. So we can look in a bit more detail at that. These sands, when you look at them in detail, they were all deposited from rivers. So they are what we call braided fluvial systems. They're channels, deposited in channels or big bars within the rivers. And in the lower one, we still get some mudstones. The black is supposed to be mudstones on here. But the mudstones are not very continuous, but they are there. If you go to the next slide, I think this one also shows you a bit more detail. The next one, keep going. Yeah, and in this section, we see some interesting things. We see mud cracks, deformed mud cracks, which suggests that the environment was very hot and arid. The red color of the rocks also suggests that. Anytime you get red rocks, which is oxidized iron, suggests that it was deposited on the surface and it was very hot conditions. And mud cracks also tell you that as well, because mud cracks mean you had water, maybe a temporary lake, it dried out, and then it cracked. We also see evidence, quite unusually, that on some of these big sandy bars, we had insects burrowing into the top of the bars. And you've got these sort of chambered burrows, probably from insects. So these bars were exposed. They weren't always underwater. And if you think of most rivers, say in India or somewhere like that, or in Australia, the rivers flow, but then they don't flow again maybe for another 1 or 2 years. So you've got time for insects to burrow in. They don't often get preserved, but they have done here. And the next one. Now, in the middle of the F5, the middle Ucmiden, this is what you want to find if you're a geologist looking for oil and gas. You want a reservoir without mudstones. We want just sand. And these are just channels and bars sitting on top of each other, and there's hardly any mudstone. A very high energy system. And the next one, I'll show you some pictures of, keep going a bit. Yeah, I think this one. So you can see these big cross beds. So these are big bar forms that were moving down the river. And you can see lots of cross bedding in here as well. So all of this suggests a very high energy river, a big river system. Probably something, people always say like the Indus or the Brahmaputra or something like that, moving down the valley. So we worked on these, and the next slide will show, I think, the model we produced. If I'm right. Keep going. Yeah. So we made a model for what it was like at different times. So we had a basin that we had a fault that was moving, that created the basin, and we have a river that's moving down the axis of the basin. We do also get evidence. I didn't show it here, but we do also have evidence for little fans coming in from the side. So we do see that as well. And then by the time we get to the middle Ucmiden, the climate must have changed. It got a bit wetter, and we have a much bigger river. And that river is much more powerful, so it's very sand dominated. Yeah, and then eventually it changes again later on. So we go from a small series of rivers to much bigger rivers. When it's this high energy, all you deposit is mostly sand. The muds all get washed out to sea. Okay, the next one just shows you that the PhDs, what their work from an oil perspective is to, when you drill a well, imagine you drill a well here, you encounter sandstones and mudstones, but when you drill a well, if you think about it, when we drill a well in the subsurface, it's only in the reservoir 8.5 inches across. So if we find a mudstone, we don't really know how extensive that mudstone is. Does it go for 1 meter or does it go for 10 kilometers? So the outcrops can help us. So we can do work on the outcrops where we can see the section, and then we can use this to help us understand the subsurface. And what you can see in here, the green on here is the mudstones. And you can see the mudstones in the main sandy unit, they're never very continuous. They only extend for 20 or 30 meters before they get cut out by sandstones. So for the reservoir geologists and the reservoir engineers, these wouldn't be a problem. You'd see them in the well, but they wouldn't create a barrier to flow. Some of the other units, we did get some units which were a bit more continuous. So we use these detailed models to build a detailed picture. Okay. Now, if we just carry on driving up here, we go past this big fault, and you notice here we've got the Triassic on this side, and on the other side we've got the Precambrian. So if we have a look at the next picture, you can see what it looks like as you're driving up the valley. So it looks very strange because where should the Precambrian be? Should it be above the Triassic or below the Triassic? It should be below, but it looks like it's above. So you've got the Triassic here, the red beds of the Triassic, and then we've got the Precambrian sitting on top of it. Well, that's what it looks like from the road. Now, that's not the case. If you do the next picture, I'll show you what really is happening. So behind here, we have a big fault. So what's happening is that the Precambrian, the Triassic was down here, the Precambrian is being thrust up and above. It's being pushed up. So it looks like the Precambrian is immediately above it, but there's a big fault behind here, which pushes the Precambrian right up. And the Triassic that was deposited on top of this Precambrian, that's already been eroded away. Yeah. Okay. And then you can carry on driving, and then we get to the top, you get a fantastic view of the real high Atlas. And in the distance, you see Toubkal, which is the highest mountain in the whole of North Africa. In fact, it's the highest mountain in the whole of Northern Africa. And you can see it's 4,167 meters high in the distance. And most of this section in here in the middle of the high Atlas, this is all Precambrian. It's all been uplifted so far that all the younger rocks have all been eroded away. Now, there is still a little bit of Triassic in here. There is some Triassic in here. So the next picture, you see these little bits of preserved Triassic, the red beds. You can always tell where the Triassic is because it's very red compared to the grey rocks of the Precambrian. Okay, and then we keep going. So what was interesting as well that the students worked on is that, you know, in crossbeds always dip in the direction that the current was flowing, the river was flowing. So if you measure the direction that crossbeds are dipping, you can work out what direction the river was flowing in the Triassic. And if you measure the crossbeds in the area we've just been, the rivers are all flowing to the east. So they're actually flowing to what is today the modern day Mediterranean. And that was, at this time, was Tethys. And we stood here somewhere and we looked at Toubkal and we saw the Triassic in the distance. And when you go over here, all the rivers are flowing the other way. So they're all flowing towards what will be the Atlantic, the opening of the Atlantic. So we have in the middle what we call a drainage divide. It's where the rivers split. These ones are all going this way and these are all going this way. Now, I'm very quickly going to take you to have a look what the Triassic looks like on the other side. So we were looking at the Triassic on this side. If we go over the big old high of the Massif Ancien, we can have a look in this basin, which is called the Argana Basin. Okay, next one. And this is the geology map of the Argana Basin, which is a bit complicated, but the purple is the Permian. There's little bits of Permian left. And all these other colors, this is the Triassic. And there's a motorway and a road that runs all the way down this basin, so you can see all this. And this cross section here is what it looks like. So you can see you've got the older Carboniferous again with an unconformity, and then you've got the Permian. We have another little unconformity, and then we have the Triassic sitting on top of that. And in fact, the nice thing about this area is you can drive from the Carboniferous to the Permian to the Triassic into the Jurassic and keep going all the way up into the Cretaceous. So it's the only place in the whole of West Africa, and in fact it's the only place in West Africa and North Africa that you can see the whole section. Because when you go further south into Mauritania, Senegal, it's not exposed. And if you go on the other side to Canada, you can find the Triassic, but nothing else. Everything else is eroded. And then if you go into North America, it's all in the subsurface. So this is the only place you can look at the geology at an outcrop. So we're running out of time here, I think a little bit. Yeah, well, we're doing okay. So what we're going to do is I'll show you the Triassic in a place called Argana. Most of you have probably heard of Argana. You probably used Argana oil on your hair or something like that, yeah? Or you cook with Argana oil. Argana oil is one of these magical oils. You can do anything with Argana oil. And Argana oil comes from Argana, this valley, or the bigger valley, because it comes from the Argana trees. They only grow here. So this is where Argana oil comes from. Okay, so let's have a look at what the Triassic looks like in this valley. And I think this valley is even more spectacular. It's not as high, but you can walk out along and on the Triassic River. So everything here, the red rocks in here, this is the red rocks of the Triassic. And we're looking sort of due west. And as the motorway runs right down this valley. And if you look in the distance, you have the little hill in the distance, or the escarpment. And this is the escarpment which has the Jurassic sitting on top of it. So that you can do a cross section all the way through and walk through that section. So this is Argana itself. We're going to have a look at this because this is the sandstone. It's the equivalent of what we've just seen in the High Atlas. We think the same age. And it's the sandiest unit again. So that's what we worked on in this basin. The next slide, please. And there's a dry river that runs through it, and you can see beautiful exposure of these sandstones. And again, these sandstones are mostly fluvial sandstones, so deposited in rivers, or aeolian sandstones. So at the same time as we had rivers, because it was so dry, when the rivers didn't flow for maybe years, then we had sand dunes blowing and depositing big sand dunes as well. So we had a mix of aeolian and fluvial. And the next slide will show you some of these sections. So we've got mudstones at the bottom, and then we've got these big pile of sand. And in fact, these upper ones, which they weather a bit differently, these ones are dominated by aeolian sands, because they're very clean sands, very well sorted, and that makes them weather slightly smoother than the fluvial sands, which are more poorly sorted sands. Okay, the next one will show you some more pictures. So, and it is one of the most spectacular places to walk in cross-bedded sand. So effectively, you can see all these cross-beds are dipping this way. So effectively, you're walking in a Triassic river, and you're walking towards the Atlantic. This river was flowing towards the basin that is going to be the Atlantic. I think if you click it once, it's a little video, mini one, but yeah. So this is with some of the MSc students out here. And everything is cross-bedded, everything. And you can walk along these cross-beds. And there's a mix in here of aeolian down here and big fluvial bars as well. So you've got a mix of big fluvial bars and aeolian. So you can imagine this river. If you've been to, I know you've been to Namibia. So in Namibia and other places, you've got the rivers flowing through the sand dunes. This is what was happening in the Triassic. Big sand dunes, but the river was occasionally reworking the sand dunes and reworking them all. Next slide, please. And again, we see evidence that it was very dry. We see these massive um, uh, got what they are now. Mud cracks, sorry, just went out of my head. These massive mud cracks. There's a hammer there for scale. So again, the mud cracks suggest that we have very hot, arid conditions at that time. So these are temporary lakes that form on the edge of the rivers, and then of course they dry out and bake in the sun, and they crack and they get preserved. Next slide, please. And then just some more examples of these beautiful cross beds. Okay, so now what we're going to do, I think the next slide is probably the end of this. Oh, one more. There are also some big conglomerates as well. You see these big coarse conglomerates. So these are some of these alluvial fans that came in as well as the river and the dunes. We've got alluvial fans coming in as well. Okay, the next slide will show. We're going to move. Oh, last one. I've got to remember these. If you imagine, the Triassic was also a time, of course, when we had dinosaurs, we had some reptiles, we had some primitive mammals. So they were walking around at this time in the riverbeds. They go into the riverbeds because they want to get water. There might be a little bit of vegetation growing in the riverbeds. So on top of one of these big sandbars, this was with some Brazilian geologists, and one of them was a specialist in paleontology. You can see here we've got little footprints. So we've got footprints of a small proto-mammal, doesn't exist now, that was walking on top of this sandbar at the time in the river. Okay, and actually in these areas they found lots of bones and footprints, and specialists we use those to date these rocks because there's nothing else in there to date them. There's no marine fossils, of course, so they used bones to date these rocks. Okay, keep going. And then this is just to say, if you want to imagine what this would have looked like in the Triassic, you just need to go to Australia today. So if you go to the central part of Australia, you've got dry desert land where for years, tens of years, decades, there'll be no rain at all. And you've got sand dunes and dry riverbeds. But then maybe every 10 years, maybe every 50 years, they get floods, and the whole of the interior of Australia gets flooded. And you get these massive rivers forming, these big braided rivers, reworking all the sands, big floods. And then 2 weeks later, a month later, the water's gone. You go back to dry, hot, arid conditions. And this is what it would have been like in the Triassic. The Triassic in Britain, when you go down to Sidmouth or Budleigh-Salterton, and this is what it would have been like in Morocco. Okay, next one, please. Now, we could probably stop there, but I just want to also show you that if you continued going through the section, we would leave the Rift Basin, the Triassic Rift Basin, because now we're going to the point at which the Atlantic starts to open. So the next slide will show you what we get. So we keep going. We're going to go from the Triassic into the blue rocks, which are the Jurassic rocks. And the first thing we see at that contact is this rock. Actually, this actually comes from a slightly different place, but it's a better looking outcrop. And this is basalt. So we have a thick basalt unit. So when the Atlantic opened, we had massive outpouring of basalts. A bit like you see now, of course, in Iceland, because Iceland is sitting on top of the mid-oceanic ridge, and we've got a lot of volcanic activity and basalt pouring out. But these basalts were, the extent of them was absolutely enormous. So the next slide will show you a map. So the place where the area we found basalts, so this is a map that shows Canada, North America, South America, and Africa, and basalts have been found all in this area. So there was a huge outpouring of basalt. So basically we broke the crust. Pangaea broke in half. We break the crust, the mantle comes to the surface, and at the same time we have massive outpouring of basalt. Now, of course, if you have this amount of basalt on the surface, we have a huge amount of degassing, massive amount of carbon dioxide into the atmosphere. So this is one of the, not the biggest, but these are the extinction events. And in the Triassic, something like 30% of all the world's species were made extinct because it changed the climate. The basalt changed the climate. The gas that came from the basalt made it poisonous. It made the oceans poisonous, made the land poisonous. So a lot of species died out at that time. And that's the boundary that we place, because of all these extinctions, that's the boundary we place between the Triassic and the Jurassic. That is what the boundary is. And then we go into a different system, because once their basalts have stopped, then we have what we call a passive system. The Atlantic Ocean is just opening, and the whole of these basins are just basically getting deeper and deeper and deeper. They're sinking into the Atlantic, towards the Atlantic. So the next slide will show that. So what we've got now, of course, a slightly different image of that, but now, because we're generating the Atlantic, which is now connected with the big ocean Tethys, we've got marine waters flooding in between what will become North America and Africa. So we have now marine conditions. So we've gone from red beds, where all we saw was red sandstones, continental sandstones, and all of a sudden now we're starting to see marine waters. So we're going to start to see limestones. So the next one will show, I think we start to see some of these limestones. So I'm not going to show you them all, but as you say, we go from the Argana Basin, which is the Triassic, then we go into the Jurassic, and we start to see limestones. And in particular, the limestones in the Oxfordian and the Calovian, we've worked on these again because these are also potential reservoirs for oil and gas offshore. So they could hold oil and gas. So we had another student working on those, and I'll just show you some pictures of what these limestones look like. Next one, I'll do. Keep going. Yeah. So this is the outcrop now of the Jurassic. All limestone, well, mudstones down here, and then limestones. And these two big sort of cliffs through here, this is the Calovian, and these are the Oxfordian limestones, really big limestones. You can find these same facies, the same carbonates, all the way down from Morocco, all the way down to Mauritania and Senegal and south. And you find them on the other side of the Atlantic. So you find the same limestones, same age, in Nova Scotia, Canada, and all the way down North America. So we had basically reefs, carbonate platforms, all the way down the Atlantic. So if you imagine the Great Barrier Reef today, times that by 10. So we had a huge reef system on one side of the Atlantic and a huge platform system, not quite reefs, but platform on the other side. And I'll show you some more photos of those now. So if we keep going, we can have a look at the carbonates. So these are the two big carbonates we're going to look at. And we're looking at these, of course, because they're the thickest carbonate. They're more likely to be a reservoir in the subsurface. Next one again, sorry. And in this outcrop, in a place called Tidili, you can actually see the lower carbonate is here, and the upper one is here. But the special thing about this one is we can see that this is actually a buildup. Because can you see that the dips of the beds, this is the dip of the beds. These rocks have all been tilted. They're in a big anticline. So we have a big anticline here. Okay, so they have all been tilted, but these rocks are dipping much steeper. So this is a structural dip. This is the fold. But these dips, these are depositional dips. This is the front of a reef or a buildup. So the next slide should show what some lines I've drawn on. So we've got a carbonate that was, they're not quite reefs as we know in the modern day, but they're buildups building on the sea floor, big carbonate reefs building on the sea floor. And yeah, keep going. So this is the PhD's interpretation of these buildups over time. They grow now because when carbonates grow, they can't grow above sea level. So once they build up, if they get near to sea level, they have to keep growing, they've got to grow forwards. So that's what happens with carbonates. They build up, and if sea level doesn't change, they build forwards. And that's what's happened here. They've built up, and then they build forwards. And you find lots of bivalves, sponges, crinoids, corals. So we've got very good evidence that this was very nice water conditions with lots of species growing. And actually, the type of corals you get, you can also tell the water depth. So in the deeper water, the corals tend to form flat discs because they need as much light as possible. Whereas when you get in the shallow water, those flat discs would get destroyed by the waves. So the same coral, the same species, instead of forming flat discs, forms mounds like this, really tough mounds. So the shape of the coral, or the shape of the corals, tell you the water depth. Okay, nearly there. I'm just going to show you some pictures of the next one. Just shows you what it would have looked like in the Jurassic. So we would have shallow water, where we get mostly, as you see, we get all sorts of, we do get some bioclastic sandstones and oolites maybe. And then we have the buildup, which we see. And in the Jurassic, these corals modern day, the corals tend to build up here in much shallower water. But in the Jurassic, they were building up in slightly deeper water. They like deeper water in the Jurassic. Okay, next one. Yeah. And the student, to show you the sort of level of detail, she spent 3 years describing the rocks, describing all the different rock types, and she built a fantastic 3D model. And this is exactly, if you're an engineer, reservoir engineer, this is what you want to be able to put into your Petrel model to build a reservoir model. It's a very detailed model. Each one of these different colors represents a different type of rock, a different facies. And also these rocks have different porosities and permeability. So she built a very detailed model. Okay, next one. Now, if we go from where we were somewhere inland, and I'm just going to, the final few pictures now, I'm just going to take you to the coast. Agadir's down here, so you can drive up. There's a coast road that runs all the way through here. And we go to this place called Cap Gear, where there's a nice lighthouse. And we see the same limestones in Cap Gear, but whereas in here we were looking at cliffs, in Cap Gear we can walk out on it. So it's a bit like we saw with the Triassic. Sometimes you have outcrops that are cliffs, which are great to get an idea of scale, but they're hard to get up. But sometimes you want an outcrop that's flat. You can walk along. So we can go and have a walk along this flat plain here. And what you see here are the corals. Really spectacular corals in the Jurassic. So you've got some students here. They're looking at all these different coral shapes. So this is, at any one time, this would have been one of the fronts of the reef in the Jurassic. It's been now eroded out. So this is the front of one of the little reefs. And of course, remember, these reefs are growing. They're building forward, then they build up and they keep building on top of each other. And this is just one of them. And then when you go and look on the top of these, you see these spectacular corals. There's about 50 different types of corals being identified. So it's a very robust colony of corals, very happily living there in the Jurassic. I think the next one shows you a couple more, I think. Yeah, all these different types, lithostration, all these other ones. You've got some names on there. I am not a carbonate specialist, so it's not my speciality to know what these are, but I know I can tell they're all different species. And you do see some spectacularly big ones. And the last one, I think, is some more in here. Corals, some bivalves, big bivalves in here. Quite a very happy community of all these species all living together in the shallow waters, relatively shallow waters. Okay, keep going. Another one, last one. I think that's the last one. Foot for scale, always. Always have a scale. Yeah. And you see you've got very large coral head in here, and we see all these bivalves in here as well. The next one shows you, imagine this would have been like, this is a modern day one, so it's not exactly the same, but you can imagine this is what it would have been like in the Jurassic. If you could swim around in the Jurassic, you'd be seeing these very large, big coral heads, huge corals growing in the water. Not exactly the same, but very similar. Okay, so that's near the end of the geology part, I think, if I'm right. If you go to the next one. Yeah, so the last bit of the geology then. So what we've seen in the Jurassic is that in the Jurassic, this area that was previously all red beds has been flooded by the sea. So the land still exists, but the land is now much further to inland of Morocco. And where we are, where we've been looking, we looked at this area and this area. This is now all a very shallow water, maybe 100-meter water depth, with corals building up and big bioherms. If we went further offshore, this is where the true Atlantic is. So we're in a shelf. And this is depositing very nice carbonates that could be reservoirs. They've actually drilled these many times offshore Morocco. They've never proved hydrocarbons in them. They've got shows, but they've always been poor reservoirs. Poor reservoir quality, unfortunately. But we're still looking. Okay, we're still looking. It's not over yet. Not quite. Okay, next one. So to wrap up, we've seen the Carboniferous underneath. We've seen the Triassic rift basins faulted, sitting on top of that big unconformity. Then we saw when the Atlantic Ocean opened and the massive outpouring of basalts, which changed the climate and killed off 30% of all the species in the world. And then once the Atlantic starts to open, the rifts stop moving. And then we also get marine waters flooding the coast of Morocco. And then we eventually get into dominantly limestones with big corals. Later on, the corals got killed off, but that's another story. So the next one, I think, just wraps that up in words. So we've seen the evolution of a sedimentary basin. We've seen the collision and creation of Pangaea, which caused the big mountain belt to be produced. And then eventually, as that gets eroded, that makes the Hercynian orogeny. Then, as it collapses, we start the rifting in the interior of Pangaea. And because we're in the middle of a continent, the deposits are all continental. They're all rivers, fluvial, or maybe some lakes. But we don't see any marine rocks because we're trapped in the middle of a continent. And it's very hot because we don't get much water in the middle of the continent. But ultimately, these rifts, one of these rifts, which became the Atlantic, breaks the mantle, the crust, sorry, and the mantle comes to the surface. And then we create an ocean. And when we create the ocean, we have the outpouring of the basalts. And at that point, the rift stops. Because now we can just push these two, or pull these two continents apart. And gradually, the basin starts to sink, and then we get dominantly marine rocks in the early part of the Jurassic. And I've shown you some reservoirs. We don't see any source rocks on shore, but we think in the early Jurassic, there's going to be a source rock deposited in the very early Jurassic, when the Atlantic was only very small, because that's the perfect time to make source rocks. Okay, and then the last few slides are just a few slides. Let me see what the next one. Yeah, I'll just show you a few more slides of Morocco, because Morocco is not just about geology. I think you should all go to Morocco for geology. I don't get paid by the Moroccan Tourist Board, but it's a great place to go for geology, but it's a very great place to go for culture. So I've just got a few pictures to show you a bit of the country. So when we go on our field trips, if we go very remotely, and I'm sure Dick Selly's probably seen all these, we've been on these sort of trips, we take four-wheel drive vehicles, often in a huge convoy. This is taking some of the oil companies to look at the rocks, slightly more remote area than I've talked about. When we go to Agadir and Marrakesh, the next one, we just take Mercedes Sprinter vans, but we often have 5 or 6 of those as well on a big trip. Next one. If we're doing geology, actually we're in pretty much Moroccan weather now, I think, to be honest, because it's very like this. And in the middle of the day, in the Argana Basin, in the red rocks, it's very hot, 40, 45 degrees. So you have to find shade for the lunch. So we sit underneath an Argana tree, and even just that one tree, that shade, will drop the temperature by about 5 or 6 degrees just by being in the shade. And then we always have a sort of a picnic lunch in the field. There's nothing better for a geologist to have spent the morning looking at rocks and then a nice picnic lunch in the field. Next one, I think, shows you. Quite often, Moroccan kids will come and say hello to you. They don't do it so much now, but in the old 10 years ago, they would be asking for stilo pens or a little bit of money, or we often used to give them, after we finished our lunch, we give them whatever we haven't eaten, you know, oranges or bread or whatever. And a lot of these people are really, very poor. And the next one, almost going to be bang on time. The contrast between the beautiful mosques and the houses in Morocco and the red rocks of the Triassic is quite spectacular. And of course, everywhere you see dotted around in Ghana, you see the Ghana trees. And they're always roughly equally spaced because they're hunting for water. So they don't grow too close together. You don't get a forest of Ghana trees. You get a dispersed group of trees. And then what you also see in the Ghana trees, which is very famous for this, the Ghana trees have the fruit of the Ghana tree, and inside the fruit is a nut, and it's the nut that's crushed to create the oil, and the animals eat the fruit. But the tree itself is an absolute killer tree. It's a bit like a bramble type thing. Here you see the spikes of here. You wouldn't believe anybody could get anywhere near this tree. And yet, as the next picture will show, the goats don't seem to have any problem at all. So in Ghana, it's famous for climbing goats. You'll see big trees and you'll see goats at the top. And of course, they're climbing up to eat the berries, to eat the Ghana. Not the nut. They don't eat the nut. Or the nut goes through them, I think, actually, to be honest. But they eat the fruit. And then the people collect the nuts and make the oil out of the nuts. Okay, and next one, I think it's the same thing.
Oil out of goat shit.
Effectively, yes. Yeah, because they're picked up after they've been cleaned. Although, yeah. And you can see, whenever you see animals in Morocco, it's not at all like UK, you will always find a person. They never leave the animals alone. So behind these group of goats, there's a little boy or a lad or a man or a girl following them. They follow them all day. They go on a walk all day. They eat the meager amount of grass they can find, maybe a 5-mile, 10-mile walk, and then they end up back where they came from. They don't own the land and they can't stop, but they can walk. And so you'll see the animals, and then you'll see somewhere there's somebody with them, always following them. And then the other thing, of course, in Morocco is, next one, I think, is the food. The cuisine of Morocco is fantastic. And the famous dish of Morocco, of course, is the tagine. And this is the sort of olive chicken tagine. These are our students this year, actually. We took them up into the High Atlas, and this is the students having I paid for this as well, having their nice tagine, their first experience of Moroccan culture. And fantastic food. And then the last couple of slides just show you the other thing, of course, is the market. So this is the Marrakesh market, and the markets with spices and fruits and all these things. So if you've not been, go for the geology. I hope I've convinced you that the geology is very good. Go for the culture, go for the food. Okay? That's the last slide, I think. Next one. Yeah. Thank you very much.